Alright, this video is going to work through course pack pages 511 to 14 or so, talking about thin-walled pressure vessels. And how is it that a pressure vessel in and of itself is a combined loading case? So looking at what we've done so far, we have dealt with structures that have been bars, wires, beams, things that are much smaller in 2 dimensions and 1 dimension much bigger. This is the first time that we're really dealing with something that's a different shape factor, and that is that we have 1 dimension much smaller than the other 2. So we have a thickness that's small. That makes this structure that in engineering terms we call a plate. And when we bend a shell into some 3-dimensional thing, like a pressure vessel, like a tank, we end up with a shell. So if we have this cylindrical pressure vessel, essentially we're going to chop it in half and do the same process that we've done over and over again, which is looking at the equilibrium of what's involved. Now this time, and we'll think of this as just simply a pressurized air tank, this pressure that we're going to say is P, it is a hydrostatic pressure. The pressure is the same in all directions, and we're going to set our x coordinate up along the long axis of our pressure vessel. So coming back to this picture, we're going to say our x-axis is this way and our y-axis is this way, and we take our section cut and we're essentially doing a force balance in the x direction. So on the one half you have this pressure P that is distributed over the entire area of the circular plane inside, where that area is pi r squared. So on the one half we have pressure times pi r squared. Okay. On the other, counteracting that, we have essentially the stress in the wall of the structure. And that area over which the force that's resisting the pressure is distributed is the area of the cut surface of the metal. So that area is 2 pi r, the circumference around the structure, times the thickness of the wall. So a force is a stress times an area. So this is the axial stress times 2 times pi times the radius times the thickness. So our force equilibrium in the x direction is our pressure times pi r squared in one direction, and counteracting that is our axial stress times the circumference times the thickness in the other direction, and we know that we have to be in equilibrium, so we can solve that for our axial stress, and we end up with the pressure times pi r squared over 2 times pi times the radius times the thickness. Pi goes away, the squared and the r in the denominator goes away, and we end up with it's the pressure times the radius over 2 times the thickness is the axial stress due to pressure loading. All right. If we then slice it in the other direction to do our y equilibrium, we have the pressure distributed over the entire face on this side that's now a square area. We're going to call this dimension the width. This dimension is 2 times the radius, and we have that same pressure. So our area is 2 times the radius times the width, and the pressure P. So we have a force here is 2RW times the pressure. And again, we think about the stress distributed over the cut face of the metal. So if we have thickness T, and again, this is width W, then the area of the cut face is, or area of a single cut face is W times T. So overall, we would have is 2 times W times T. And this is not our stress in the axial direction, but we call it sigma theta, which is our stress in the hoop direction of this cylindrical pressure vessel. Again, force balance now in the y direction. We have 2RW times the pressure, and counteracting that, we have this hoop stress times 2 times width times thickness. That has to equal 0. Solving for the hoop stress, and we get 2RWP over 2WT, and that is PR over the thickness. So in summary, we have the axial direction, which is, if this is our pressure vessel, we have axial direction, the stress is PR over T, and we have the hoop or y direction, that this stress is PR over T. Or, in another way, we have axial is 1/2 times the hoop. This is for cylindrical pressure vessel. If we look instead at a completely spherical pressure vessel, which is a little less practical to manufacture or deal with, but we can see that because of the spherical symmetry, any cut in any direction is going to yield the same thing. This time, the cut face area, 2 pi r times the thickness, and the entire area of action is pi r squared. If we sum these forces, we will have the pressure times your pi r squared minus the stress in that direction times our 2 pi r times thickness. And just like the axial case for the cylindrical pressure vessel, these cancel, we end up the pressure times the radius times twice the thickness, and that sigma y is the same due to symmetry. So for a cylindrical pressure vessel, you have the axial is half of the hoop, and for a spherical pressure vessel, you have the same in any direction that you would slice.